I'm Alex.
I'm Jacqueline.
Our two other group members, Evan and Bev, couldn't be here today, but our project is the HDMI-based simple graphics processing unit. So our sections for this presentation is just our project goals and specifications, overall system architecture, specifically the host and GPU interface, how we use HDMI output to our display, some video demonstrations of what we have so far, some RF emission measurements that we're using to gauge FCC compliance. Yeah, okay. Oh, wait. To share the screen. Yeah, so RF emission measurements to gauge if we're FCC compliant or if our device could be FCC compliant, and then our system testing and documentation. So our project goals and specifications. The goal is to design and create a rudimentary graphics processing unit, or also known as GPU, to drive HDMI connected display. We must be able to display at 1280 by 720 resolution at 55 megahertz, which is about 60 frames per second. We want to have a color resolution of 8 bits per pixel. That's 3 red, 3 green, and 2 blue bits. We're interfacing with a PSoC board to receive commands, such as a rectangle fill. We're carrying out extensive verification at multiple levels, and we're carrying out the FCC certification procedure, but not actually going through with it. We're just going through the motions for it. And our constraints are that we have 1.68 megabytes of onboard RAM, and that leaves roughly 1 byte per pixel at our color resolution. And all this must be accomplished using a Nexys video board. So the main equipment used is pretty simple. It's a PSoC 5LP development kit on the left. This is our host device, which is like the stand-in for your computer. An HDMI monitor or any HDMI-driven display, and the Nexys video board. And this is where all our actual data processing gets done. So here's our overall system architecture. So you can see in the PSoC section, that's your host computer, where we have a simple host application running that just passes data that it has to the host or to the GPU. That goes through a host interface, some command queue, and a command processor to eventually get stored through registers into display memory. And once it's in display memory, the display generator continuously reads from memory to output through the HDMI block that we have to a display monitor. So our host and GPU interface, this is just a kind of zoomed in slice of the previous system architecture. The way that we send data is that we send 5 bytes in a row. The first byte is an address byte to let the GPU know which register to store the next 4 bytes in, the payload. They're stored at their specific register address, and registers can hold color data, coordinate X and Y values, and other key info like test pattern mode or this thing that we have called an engine trigger. And a total of 5 register writes are needed to draw one shape. As we need a top left position for specifically a rectangle, a top left coordinate, a bottom right coordinate, a color, a test pattern mode, and an engine trigger. So this is kind of more specifics on the implementation of how our host GPU interface works on the first block, which is the FPGA host interface. Basically, we have a simple state machine that uses 2 signals in both the host and the FPGA that so that they can kind of handshake back and forth. So the GPU waits in state S0 at an idle state until the host sends some data in which its handshake signal will change. And on that change, it'll transition to state S1, where the data that the host is sending to the GPU actually gets saved. And then it transitions back out of state S1 to state S0 by toggling its own handshake signal. And you'll see next that we have some waveforms to show how this works. But it's essentially just communicating with 2 signals that run between the boards. And this is just some Verilog code of how it's actually implemented. Pretty simple always loop. Basically, if the state is in S1, then we update the host handshake signal. and if the state isn't S1 for the on the GPU, we toggle its own handshake signal as well. And then here we just send the data if it's specifically in state S1. Here's just some waveforms to show how this works. So we have our clock and our reset signal. So the host is sending 0, 0, then 0, 1s, and then 0, 2. And it only actually saves the data, which is on these little X like transitions, if the two handshake signals are the same. So here we see little state transitions, little one cycle chirp. Whenever those happen on the next cycle, the data is actually transferred. So our display memory. So once the data goes through the first two blocks, it goes through the register block. The register block is actually parsed by the display memory block to receive data from the registers, like the coordinates, the color, and the specific command we're doing. This selects the appropriate engine to write with based on the engine trigger and then sends a start pulse. So for example, right now, we only have a rectangle draw engine, but that can actually do quite a bit. And this specifically writes to the VRAM using the coordinates and the color given. This just updates a section of our VRAM. So the rectangle fill engine, it activates upon receiving the start pulse sent from the video memory. It goes from an idle state to an active state when it's actually drawing. This implements an X and Y counter that increments from the top left coordinate to the bottom right coordinate. So we're only filling in like this specific yellow range. We calculate the write address using this equation of Y times 1280 plus X, and that's just updating the VRAM at that specific address. So our test pattern and rectangle engine state machines. Test pattern is just another mode that we have. It's kind of more implemented just on the GPU. We can just display any test pattern procedurally without having to actually send the data. Upon the system start, a test pattern is displayed on the screen. So this just happens automatically whenever we start it right now by design, just to have a background. So once the drawing is finished, the test pattern engine moves to an idle state and then waits for any other engine to start. So we start out with like a checkerboard pattern, as we'll see later, and then we can draw rectangles on top of that. So our display generator, this increments across the entire display, incrementing counters and X and Y counters to the read address to determine the read address. And this reads data from the virtual memory and outputs through the HDMI. This implements blanking to give space for the generator to restart and read a new row for the VRAM. It just needs time. This is pretty standard. We pad the right side and the bottom with just some extra space or some extra like cycles, where we drive an H blank signal when we reach the end of a row, and we drive a V blank signal when we reach the bottom of the monitor. So an example of a rectangle fill command. So you can see we have test patterns, a blue and black checkerboard to start out with, and then we sent this command or a command to draw some rectangles. So for the blue rectangle, the top left coordinate is 250, 150. So that's 250 to the right and then 150 down. And then the bottom right is at 650, 650. We sent a hex code for the color that we want, which is 2 red and 2 green and 2 blue bytes, or 1 byte for each actually. So then we send a 0 for test pattern, 0 for engine ID, and that's just like specifics on our implementation. But that eventually gets stored into the registers. The blue color is written at all those values in VRAM, and then it's actually read out and displayed on the monitor. So our system performance, the maximum pixel drawing rate is 74.25 million pixels per second. And this is because the clock speed of the FPGA is 74.25 megahertz. And our estimated max command rate that we could send is about 29,400 commands per second, just on this calculation from our experience and the measurements we took during our testing. So this is an example of a circle that we drew, but so as I said before, we only are able to draw a rectangle right now. So this is actually 360 really small rectangular squares, basically, organized into a circle pattern. It's just done using a script to generate the data for the squares first, and then we just send that through our host. So here's an example of just a little animation we did. This is the same circle command. It's just now we're procedurally updating the colors. And this is just done through a simple modification of the host application. We can make it go faster. We can add more colors. So we can both set the data explicitly or just procedurally update it. So in this animation, we just do a sweep from the top to the bottom, showing the RGB values. And this kind of shows explicitly that our red and green values have more color depth than the blue. And this is by design just to keep it for 8 bits of color. And yeah, you can see there's like a couple, only a few blue lines versus the same amount for the red and green. So for our RF emission measurements, so initial measurements we took previously from on a spectrum analyzer shows a peak at 74.25 megahertz, and this agrees with the clock speed of the board. The signal power is averaged in this measurement just to reduce some noise, and we're currently setting up a new antenna to get more accurate results without having to average and get rid of noise explicitly.
For system and testing documentation, a Python program was written to create a dashboard. As you can see this is the dashboard right now. We on the left we have the test names, in the middle we have the description of the test, and then we have a column that says whether the test was run or not, and then the status, whether it passed, failed, or it hasn't been X was not been tested or not run. So there's no status. On the bottom there's like a report that tells us whether the test has been run and passed, whether it has run and failed, whether it had any entry errors, or whether it has not been run and other entry errors. Right now, like this would be like the final, like our final goal would be to change to the right the color of the text. Y would be green, and would be red, so that's the only thing that needs to be changed. But other than that, this Python program reads CSV files and outputs this to like have everything under like one specific file to see like who's tested certain things or not. Wait,
yeah.
Okay. We also have a project website where you could find out more about our senior project. There's like our team members' information, our past minute meetings for our whole like semester worth of project, as well as other documents and presentations for our project.
So yeah, so the next steps of our project are we want to implement an image download and display command so that we can just upload an image to our host device and then have the GPU just print that out. And then hardware line drawing. So this, we can draw, like, instead of just drawing completely horizontal or vertical lines, we want to be able to implement angled lines or maybe even curved lines at some point. But that would be, that's for more work. So, any questions? Yeah.
So you're talking about the curve. Is that what you have in the circle, or is that still?
Yeah, so the curved line, the circle specifically is a bunch of 32 by 32 squares that we just have printed out, and it looks like a circle. Yeah, so like on like the limit of it, we could print like a 1 pixel, square,
Yeah.
and then print that in a circle. But that would be like just saying that's using our rectangle engine. Hardware line drawing would basically just be another engine that would use an algorithm called Bresenham's line algorithm. That it just based on like it's specifically for drawing lines and not knowing like exactly what you have to print off the bat. You just take like a start and end coordinate, and it basically gives you values you should print. So yeah.
This is also like this project, right?
I don't think so. We haven't actually had any talks about that. It definitely could be. Like, there's a lot of work that can be done with it. I think
Polishing, and just as we were saying.
Yeah.
Implementing types of features, this would be something for a future project.
Yeah, I don't think it's definitely not for next year, but it could be something in the future. Like, this is actually really similar to a previous cruise project from, I think, just 2 or 3 years ago. So it's definitely in the vein of something that people would want to improve on. So
How you guys figuring this stuff out?
yeah, a lot of help from our professor.
Okay.
He's like kind of like a Verilog whiz. So figuring out the Verilog behind it is a lot of work talking with him, but also a lot of just testing and running like a lot of tests to see if it works. And we're testing at every single step, basically. But so, yeah, it's basically just yeah, it's just a lot of work with our professor and just basically reading on how exactly GPUs work in general.
And that's, yeah, that kind of follows it. So this is more of like an educational exercise, it's like a practical use that you're.
Yeah, this isn't going to be going to any consumers or whatever. This is
Yeah.
just for us to figure out how like the basics of a GPU work
Yeah.
and how your computer actually like displays something on your screen. So yeah. All right. So that's about it.